Thank you very much for the nice invitation to give a talk here. It's a pleasure. I also don't have something depending on time, but speaking of an obstacle problem is a bit on free boundary, one can say, where we touch the obstacle. So what I'm going to speak about is a joint work with Marius Müller from the University of Freiburg, Shinya Okabe and Kensuke Yoshizawa from Tohoku University in Sendai, Japan. So let me first introduce the energy we are going to consider. So we take a parameter P between 1 and infinity, and we define the P elastic energy as the elastic energy of the graph of U. So U is a function defined one-dimensional, defined in the interval 0, 1 with value in the real number. And the elastic energy is the integral of the curvature to the power P integrated along the graph. So here the S is integration with respect to the arc length parameter given by the curve, given by the graph of U, and K is the curvature of the curve. So today in this talk, I will consider especially this type of energy, this P elastic energy, but part of the work I'm presenting today, we can do also with some generalized energy that have the same structure. But for the talk today, we concentrate on this energy. So this energy for P equal to 2 is quite famous for describing the elastic energy of rods. And now we are looking at the generalization to P different from 2 and between 1 and infinity. So the problem we want to study is an obstacle problem. So let me try to see if I can, if now it's a bit, now you see all the slide. Yeah. It's an obstacle problem. So we consider a function psi, that what we want to think of as an obstacle that's defined in the interval 0, 1 is a continuous function. And we assume that at 0 and at 1 is strictly negative, but at some point in 0, 1 is strictly positive, so that we are really becoming positive somewhere. And we are looking for function u for which the energy is defined. So we want to look at function W2P such that they are 0 at 0 and at 1. So we have Dirichlet boundary value for u, and we have the extra constraint that we stay above the obstacles u. So u has to say stay above this obstacle psi on the interval 0, 1. The fact that we assume here that psi is somewhere strictly positive ensures that the function u is identically equal to 0 is not allowed here. So we have a non-trivial problem. And what we are interested is to look at the minimization problem for the P elastic energy on this set. So does a minimizer exist? Which property does it have? That's kind of the general question we are looking at. So let me first tell a bit what some previous works on this subject. So the case P equal to 2 has been studied. So in a co-work with Klaus Deckelnick in 2018, we have first shown some first existence and non-existence result. So here you see some plots. In red is the minimizer computed numerically, and in blue you see the shape of the obstacle, and you see some feature that we will also see that the minimizer is always concave. We are always going to touch the obstacle, and you also observe that when here the obstacle in this third picture, when the obstacle is quite big, we see that at the boundary, the graph gets very big slope. So we expect, so that's why we have non-existent result. When the obstacle will become big, then we will not find a minimizer anymore in the class of graph, because some vertical slope will appear at the boundary. So the question is, for which obstacle do we still have a minimizer in the class of graph, so not with infinite slope? Some sharp result on existence of minimizer has been proved independently by Marius Müller and Tatsuya Miura, and they show some sharp existence and non-existent result in the special case that the obstacle is a cone. So it's as here, we have this shape. So we have, sorry, I'm moving the zoom commando here. So we have here affine linear function that are symmetric. We have a tip at x equal to 1/2. And then in this case, the minimizer will touch the obstacle at the tip of the obstacle. So the geometry is more clear. In this situation, one can exactly show when a minimizer exists and when it doesn't exist. And Bruno and Okabe studied also Dirichlet boundary condition. The problem of the flow for this kind of problem is quite new. It's quite open. There are some results for the flow of the p-elastic energy without the obstacle. And there are some results on the obstacle problem, but still a lot can be done there. So let me concentrate, which is the question that we are interested in. We have an obstacle problem, so we expect the minimizer will touch the obstacle. And we know that when we touch the obstacle, there will be loss of regularity. In this case, we have also an Euler-Lagrange equation that has a non-degeneracy due to the presence of this p power. And then the question that we try to answer that motivates the start of our study was mainly, what causes the loss of the regularity? What's stronger? Is it the obstacle or is the degeneracy of the equation? And that's kind of the main question for the talk of today. Let me say that Watanabe, that was also named in the previous talk, in 2014, computed the critical point for the p-elastic energy also under a fixed length constraint. And what you see here is a plot of critical points. And what is special about this critical point for the p-elastic energy in this case is that you have this flat part. So there are some flat core, so some straight line, part of the solution that can be joined to curved part of the solution. So these are critical points. So there is really a flat core, so this flat part appearing. So there is some loss of regularity here where the two parts of the critical point join together. And then we wanted to ask to see if such a feature, such flat part will appear also in the obstacle problem or not. And of course, another question is, can we understand when minimizer exists and when they do not exist? So which has the challenges in this energy that we are studying. First, the energy is not coercive. Due to the nonlinearity of the energy, it is a higher order problem being on the curvature. So the Euler-Lagrange equation is a fourth order problem. And then we have the degeneracy of the Euler-Lagrange equation for p bigger than 2. So what can help us to find, hopefully to understand this problem is a nice feature that happens for p equal to 2. There is a so-called Euler substitution, because even Euler, in his age, knew about that. He noticed that looking for the elastic energy for p equal to 2, so when you look at the curvature square, if you make this substitution, so instead of looking at the curvature, you multiply the curvature by 1 plus u prime square, and of that you take the fourth root, so k times this quantity, then the Euler-Lagrange equation becomes a differential equation of second order for the function d. So we are going from an Euler-Lagrange equation that is fourth order in u to a second order equation for v. And then when we have a second order equation, we have maximum principle, we have comparison principle, so we have more methods at our disposal to get estimates. And so the first question is this nice feature that appears for p equal to 2. Is this generalizables can be done also to other p? So is there an analog to this Euler substitution also for general p? In order to get from the fourth order equation to a second order equation. What is important, I didn't stress it, is that the second order differential equation has no term of order 0. So it's only term depending on the second derivative and the first order derivative, and the term with c times u, where it appears in a general second order differential operator, is not there. So c is identically 0. So we don't need to be careful what sign does it have. So do we have this feature also for general p? So for looking at that, let's compute the first variation of the energy. So I don't want to look exactly at the term, but the first part here appears when differentiating the second order part of the curvature. Here you see this power, second derivative of u to the power p minus 1. And the second term is the one depending when you differentiate the denominator. Let's say this term depending on the first order derivative of u. Okay, looking like that, it's quite nice. You immediately see there is a term depending on the second order derivative of phi and a term depending on the first order derivative of phi. There is no term depending on your phi. That's because of the energy. But then what we see is that if we can factorize this term, is here, and the rest can be seen as the derivative of this quotient. So what the term that I made this circle now in red, that is the natural generalization of Euler substitution for general p. If we think that u is a function w2p, then this function w is only integrable to the power p divided by p minus 1, but it's so an integrable function to that power, and that will have the role of our of Euler substitution for p equal to 2. So we have it also for general p. Here we define it with a minus, and the reason for that is, as we will soon see, critical points are concave, so the second derivative of u is negative, and so to have it positive, we make a minus in front. Okay, so we have Euler substitution also for general p. With what can we work? So we have an obstacle problem. So the first thing that the calculus operation gives us is the variation of inequality. So if you assume that u is a minimizer, then we take variation, non-negative variation, so that we remain sure that we stay above the obstacle. We compute the first variation as we did it, that is bigger or equal than 0, and we have this structure. What happens here is what here is in red is our minimizer, that we know that where we don't touch the obstacle, we can move in any direction. So there we will have really a differential equality. We have a differential inequality at the points like here or here where they touch the obstacle. In other words, using the Ritz-Markov-Kakutani theorem, we can say that there exists a random measure mu that is supported in the so-called coincidence set, so the set where the minimizer coincides with the obstacle, such that this measured valued Euler Lagrange equation is satisfied. So here appears the measure, the mu, this is supported where we touch the obstacle, and that is the Euler Lagrange equation with which we can work. So this will be satisfied by the minimizer. In general, we are interested in regularity of critical points. So we define as a critical point for the p-elastic energy as a solution in our admissible set, so that we keep above the obstacle of this measure valued Euler Lagrange equation, such that this equation is satisfied for all p, for all phi in W2P intersection W1P0. And now the question is, if we have a critical point, which regularity does it have? Can we understand which qualitative property does it have? So here we come to our main regularity result. For P between 1 and infinity, and assume that U is a critical point for our P-elastic energy, then we can say that U is twice continuously differentiable, is strictly concave, so the second derivative is strictly negative, is in the open interval 0, 1. So there are no pieces of line, not even no pieces of line, second derivative cannot be somewhere equal to 0 except at the boundary point where it is 0. So inside, in the interior of the interval, the second derivative is strictly negative and at the boundary it's 0. And what about further regularity? Here the value of p make a difference. If p is between 1 and 2, then the critical point is going to be W3 infinity. So third order derivative that are at infinity. The third order derivative are even BV function of bounded variation. But the function u is in general not C3. So we can find example of obstacle such that the critical point is not going to have continuous third order derivative. Whereas for p bigger than 2, then the regularity is much smaller, so it's much we have much less regularity. The function u is just W3q with q in this interval, so between 1 and p minus 1 divided by p minus 2, and the function u is never in this regularity class. So, and I would like in the rest of the talk to give an idea of our proof of this regularity result. And through the proof, we will see that for p less than or equal than 2, the obstruction to the regularity is due to the obstacle. So the fact that we can find examples where the solution is not C3 is considered particular obstacle, whereas for p bigger than 2, that's the equation. Is the degeneracy of the equation that doesn't allow the critical point to be more regular. So for p less than or equal than 2, the obstacle is the one that obstructs the regularity. For p bigger than 2, that is due to the equation. Okay, so how do we prove this result? The first step is to first improve the regularity of Euler substitution. We have a second order differential equation in weak form for Euler's regularity, and then taking appropriate test function, we can see that Euler substitution is W1 infinity. So notice the relation between Euler substitution and U. So it's not that we can immediately translate the regularity of Euler substitution into regularity of U, or of the second derivative of U. It depends on the power that we have there, what we can transfer from W to regularity of U. So we first work with the equation for W, and we are able to show that W is W1 infinity. Then we get the W has to be 0 at 0 and at 1, so at the boundary point of the interval. That is not surprising, thinking of the variational problem that we are considering. We are working in the interval 0, 1. We have an obstacle that is not active at the boundary because we asked at the boundary that the obstacle is strictly negative. And then asking that the function u is 0 at 0 and 0 at 1, and looking at critical point, then from the variational problem we get the so-called natural boundary condition, that is in some sense that the second derivative of u has to be 0, and that's exactly what we get for Euler substitution. And third, we derive thanks to this regularity, we derive a pointwise almost everywhere equation. So we find that there exists a function a positive and a function m that is decreasing and locally constant where we don't touch the obstacle, such that the derivative of w is equal to the function m. So explicitly the function m is the measure of the interval x1. So we measure the set, the measure of let's say, connected with the measure of the set where we touch the obstacle. So we have this pointwise equation from which we will derive a further regularity property. From this regularity of Euler substitution, we immediately see that u is twice continuously differentiable, and the second derivative of u at 0, and then in 1. Now, the next property that we want to show is that the function u is concave. That, in other words, that w is bigger or equal than 0 in 0, 1. Why is that? So, in other words, we have been working replacing u by its concave envelope and show that the elastic energy becomes equal or become even smaller, so that we can work with concave function. Here we work directly with this measure-valued Euler-Lagrange equation. Why is that? So since m is decreasing, we can find a point C such that m is bigger or equal than 0 in 0C and otherwise smaller or equal than 0 in C1. So it's a decreasing function almost everywhere. Then, since m gives us the sign for w prime, since the function a is positive, then we see that w is increasing in 0C and decreasing otherwise. This, together with the fact that w has to be 0 at the boundary, it is 0 in 0, it has to increase, then decrease and become 0 at 1, then we see that w has to be bigger or equal to 0 everywhere, and hence, from the formula, we see that the second order derivative of u has to be smaller or equal than 0. So we are concave. Okay, so u needs to be concave. But much more, actually, we want to show that we are non-degenerate. See, look at the relation here. We have the second order derivative appearing to the power p minus 2. So we will like that this is never 0, right? Thinking of the elliptic operator that appears then in the differential equation. So why is, so that's kind of a crucial step. Why are we 0 only at the boundary? And all is again can be derived quite elementary as before from this Euler Lagrange equation. As before, there exists a C such that w prime is bigger or equal than 0 in 0C and smaller or equal than 0 otherwise. Then we integrate, and then we see that w has to be, let's recall that w of 0 is equal to 0. So from this formula, we see that w has to be increasing in 0C and decreasing in C1. Since w then is first monotone increasing and then monotone decreasing, then it can attain a point, a value, or only at a point or in an interval. Since it is 0 at 0 and in 1, then it can be 0 only in an interval containing 1 joined with an interval containing 1, what did I say? In an interval containing 0 joined with an interval containing 1. So this we know. So let's assume that we are in this case. So there exists an alpha 1 strictly positive such that w is identically equal to 0 in a small interval containing 0. Then the derivative of w will also be identically 0 in that interval. Okay, then we go again back at the differential equation. That means w prime is 0, near to 0, and that is equal to m, that is a decreasing function. That means m has to be smaller than equal to 0 in all the intervals 0, 1, because near to 0 is smaller, is 0 actually, so it will have to be non-positive in the entire interval. Then we go back again, now that we know that m is smaller than equal to 0 in the entire interval, that w prime has to be smaller or equal to 0 in the entire interval. And hence, since it is starting being 0, then hence v has to be identically 0. From that, we follow that the second order derivative of u has to be identically 0, but since we have to be 0 at 0 and then 1, then u has to be identically equal to 0. That is a contradiction because we have to stay above our obstacle. And hence, we cannot, the second order derivative is allowed to be 0 only at the boundary point, not in the interior of the interval. Okay, so what can we say about the coincidence set? That is always non-empty. We are always going to touch the obstacle somewhere. And that is a direct application of the maximum principle. If that will not be true, if we wouldn't touch the obstacle, then we will be solution of the differential equation with a zero right-hand side without term of order 0, with zero boundary condition. Then maximum principle tells us W has to be identically equal to 0. The second derivative of U then has to be identically equal to 0. But since we are 0, both 0 and 1, then U has to be the straight line. That's again a contradiction. So that cannot happen. And okay, then let's with this observation, then we can achieve the regularity result on our critical points. In the case P between 1 and 2, then U is W3 infinity. Why? We know that Euler substitution is W1 infinity. And now we look at the power here appearing for the second order derivative, that is a power P minus 1. And for P between 1 and 2, the function taking this 1 over P minus 1 root is locally Lipschitz, also at 0. And then we can immediately turn the regularity from W to regularity in U. That works only for P smaller or equal than U, since otherwise the P minus 1 root is not locally Lipschitz near 0. It shows that we are W1 infinity. And why we are not C3? This we can show taking the special case of a symmetric cone obstacle. So this is our the cone obstacle C, that is an obstacle to straight line joined at the tip, at the point here 1/2, that's why it's symmetric. And then in this case, we can show that a critical point cannot be C3. Again, from looking at the Euler-Lagrange equation. Why is that? Since the point where the critical point will touch the obstacle will be at the tip of the cone, of the obstacle, since we have a cone, will be at the tip of the cone, that's the point 1/2. Then the measure that gives the right-hand side from the differential equation, it supports only the point 1/2. So that we have that AXW prime is equal to a function n that is locally constant where we don't touch the obstacle. That means we are equal to a constant C1 in the interval 0, 1/2, and then possibly another constant in 1/2, 1. If U will be C3, then W prime, since it's connected through this relation, will be continuous. That means that the constant C1 and C2 needs to be the same. Then D is monotone because M would have a sign, so M would be given by a constant, positive or negative. That means that W has to be monotone, but being equal to 0, 0 and 1, the only possibility that we have is it is identically equal to 0, and that is again a contradiction. And then we cannot be C3. So every time we look at a critical point where we have this cone obstacle, the critical point cannot have continuous third order derivatives. I also, in the statement, have that in this case, the third order derivatives are dV. I didn't give a proof here, but the arguments are quite similar to the argument that are coming now for the case P bigger than 2. Quite similar, so I decided to present those. What happens for P bigger than 2, then we have W3 cubed for Q smaller than P minus 1 divided by P minus 2, and we are not, the third order derivative are not integrable to the power P minus 1 divided by P minus 2. Why is that? So since W is W1 infinity, and the function taking the P minus 1 root is locally Lipschitz away from 0, away from the boundary, we are W1 infinity lock. So the problem is at the boundary point. At the boundary point there, the obstacle is not present because we assume C to be strictly negative, so that comes the problem from the Euler-Lagrange equation. And so we concentrate near 0, so to see what happens near the boundary, and we make a direct computation, and we see that the third order derivative of U behaves like W to this power. So now it becomes to study how W to this power behave. And again, looking at the Euler-Lagrange equation, we are in a neighborhood of zero where the obstacle is not there. That means the right-hand side is simply a constant that we can argue that is different from zero, again, due to the non-degeneracy of the equation. Okay, now we have an expression for W prime. Right? W prime is B1 divided by A. For A, we have uniform bounds. That means that we can say that W prime is bounded between two positive constants. That means that W grows as a growth, that is two growing, is a growth between two straight lines. And that is exactly what we are saying here. W is has control growth between these two straight lines given by two constants, d1 and small d1 and big d1. And then what we are interested in is taking 2 minus 1 divided by p minus 1 power, and be careful, p is bigger than 2. And then we know what can we integrate is every exponent that is bigger than minus 1. And in order that the exponent is bigger than minus 1, we need to have this bound on the exponent. And this gives the optimal regularity for p bigger than 2. Right, so that's about the regularity of critical points. And then perhaps as last, for symmetric cone obstacle, we have an optimal existence, non-existence result. So there exists a constant H star, such that if the obstacle is below this constant, then there exists a unique minimizer of the p-elastic energy in the class of symmetric functions, free graphs. And if the obstacle is bigger than this constant, then there is no minimizer. And thank you very much for your attention.
Thank you very much for the nice talk. I'm asking if whether there are comments or questions.
I have one question.
Yes, thank you.
May I?
Yes, sure.
Okay. Well, I enjoy very much your talk. Very interesting and difficult problem. Let me ask you, maybe, which is also a very difficult question, but maybe you have some hint to not to give an answer, but some try to answer. I see that there is a critical value that sometimes you have uniqueness and then non-existence even. So do you have any clue about if you change the obstacle somehow in which of those classes or for which topology you have at least a kind of local continuity of the critical point?
Continuity in what? Sorry?
I mean, if you change the obstacle, okay, you'll also change the solution, of course.
Yeah.
Of course, it depends if you are near the critical value that there is no existence, of course, should be unstable, I presume, of course. Mm-hmm. If you are inside the zone where you expect that at least there exists a critical point, even in some case maybe unique, do you expect at least some kind of local continuous dependence with respect to some topology in change of the obstacle?
Okay. So that's of course is a, yeah, as you said, is a difficult question. It also depends on the class where we work on. So there is so the problem is also when can you show that the minimizer is symmetric, right? That's already a difficult question. So in the case of this cone obstacle, we are able to show up to this critical A that the minimizer is symmetric, and is the unique symmetric minimizer. Marius, so one of the co-authors, Marius Müller, has a nice argument using Talenti inequality, rearrangement inequality, to show that for small energy, sufficiently small energy, then the minima, one can choose a symmetric minimizer. Actually, that's the statement, right?
But for instance, do you know if that symmetrical minimizer, is it stable if you change a little bit the obstacle?
So I would like to say yes, but I'm sorry, I cannot. So I have no still. So the problem is we have so little understanding that I have difficulty positioning myself. There are also other cases where we thought with the Dirichlet boundary condition we can show continuous dependence, but there are examples of non-uniqueness. So sorry, but it's yeah.
It's a very difficult question. I know.
But thanks. Perhaps Marius can add something. I think Marius is there. So.
Okay, thank you.